between independent photons and how we can use this possibility to produce, in fact, quantum entanglement between independent particles. Let me start by reminding you some of the well-known things. The classic Young's interference experiment, where we have a source of radiation here and the light goes through the two pinholes, and on the screen one observes the interference pattern, and one could in fact work out the conditions for the existence of the interference pattern on the screen, and the visibility of the interference pattern is related to the correlation of the electromagnetic fields at the pinhole P1 and at the pinhole P2. And if such a correlation is non-zero, then you definitely have the interference pattern on the screen. On the other hand, if the light at these two pinholes is completely incoherent, then there is no interference. The Young's interference experiment has produced a lot of excitement over the last 2 centuries, and today we have many different versions of the Young's interferometer. People have done these kind of interference experiments with single photons, single electrons, neutrons, atoms. One could also think of doing an interference experiment where you actually replace each of these pinholes by microscopic objects like atoms. So, let me first tell you the great interest that people took in doing these experiments with single photons. And here are some results of the experiments done with a very, very weak source of light. And let me warn you that a very, very weak source of light is not equivalent to a source of single photons. So when you have a very, very weak source, you hardly see anything on the screen. You would see few random clicks on the screen. If you increase the flux of the source, you start seeing more of these clicks on the screen, and eventually, if the counting time is long enough, then you start seeing this standard interference pattern with very feeble beam of light. A very nice experiment with single photon source, that is a heralded source of single photons, and this is a down conversion source which produces pairs of photons, and you detect one photon, and that heralds the arrival of the second photon, which you use in the interferometer. And such a nice experiment was reported in this paper by a French group, and what you see is a very, very nice interference pattern on the screen, and it looks very similar to what you would get with either a feeble beam of light or even with a classical beam of light. So as far as this observation of the interference pattern is concerned, there is really no distinction between a single photon source and a very big beam of light. Now, of course, in quantum mechanics, we can understand this interference in terms of two different pathways which contribute to the intensity at the detector. So the photon can go either through the slit 1 or the photon can go through the slit 2, and the intensity pattern at the screen is obtained by adding these two pathways coherently. Okay, now I want to discuss the question of interference between independent photons. For many years, it has been thought that the interference between the independent photons is not possible. Whereas I want to show to you that the interference between independent photons is possible, provided you change your experimental setup and you change your measurement scheme, you decide to detect quantities other than the intensities of light. Now we had discussed this possibility in a paper done with Herbert Walther, that if we look at the intensity correlations rather than just the measurement of the intensity, then this would be a probe of the interferences between independent systems. So let me remind you of a beautiful experiment which was done in the context of radio astronomy by Anne-Marie Brown and Twist, and what they were studying the diameter of the stars, and they discovered that a much better way to study the diameter is by looking at the intensity correlations. And in fact, if you look at Glauber's quantum theory of optical coherence, such correlation functions play a very important role in the theory of optical coherence. Since I am doing everything quantum mechanically for quantum fields, so let me remind you what is actually measured by a photodetector. We say that the photodetector works by the absorption of photons, and therefore the quantity which is measured by a photodetector is this normally ordered correlation function. So if you write the electric field operator as a sum of the positive frequency part and the negative frequency part, then the quantity which is measured by a photodetector is this, which is not the same as just the square of the real field. So that is the distinction in the quantum theory versus the classical theory. And so if we look at the program of Glauber, in his theory he introduced a bunch of correlation functions for the electromagnetic fields. You have the lowest order correlation function, which basically gives you the intensity of the field, and the traditional spectroscopic measurements all have been based on this quantity. This is the intensity correlation, and because we are dealing with quantum fields, so we have these basically creation operator for the fields here and the annihilation operators for the fields here. This is the quantity which was measured in the classic experiment of Anne-Marie Brown and Twist using the classical sources of light. In the laboratory, one could think of a very simple measurement. You can take a light beam, split it into two parts, you may put a detector here, and look at the cross correlation between the outputs of these two detectors. And this is the way one would measure the intensity correlation. Now, it also turns out, and this is very important for a lot of work in quantum optics, that what we call the non-classical fields, one can use the intensity correlations to find out whether a given field is non-classical or not. And in fact, certain scaled quantity for classical fields typically would have this kind of a behavior, and if this scaled quantity lies in this region, then we would conclude that the field is non-classical. Okay, so let me now come back to the question that whether the interference between two independent photons could be possible. So let's consider a source of two atoms, an atom located here and an atom located here, separated by some distance d, and let's assume that the atom is excited by a short laser pulse. Similarly, this atom is excited by a short laser pulse. And now in the far field, you put two detectors, 1 and 2, and do a correlation measurement. Make a measurement of the intensity correlation. So this is different from what one would do in a normal interferometric experiment, where you would only measure the mean intensity in the far field. Now it turns out, and do a correlation measurement. Make a measurement of the intensity correlation. So this is different from what one would do in a normal interferometric experiment, where you would only measure the mean intensity in the far field, in the measurement of intensity. Now it turns out, on the other hand, that when the atoms are excited by a laser pulse, and if you just look at the intensity in the far field, the mean intensity in the far field would be the sum of the intensity radiated by this atom and this atom. So there are no interference effects in the measurement of intensity. On the other hand, if you look at this intensity correlation, R1, R2 here, then you find that this has this kind of a structure, and this has a sinusoidal structure. You see the interference pattern here, depending on the locations of the two detectors. And change the position of the other detector. So depending on how you position the two detectors, if supposing effectively you have one detector, but you are still measuring the second order correlation, then you have no interference here. Then you have this interference pattern. If you move one of the detectors fixed and change the position of the other detector, then you have this interference pattern. Also depends on how to locate your detector. If you move the two detectors in the opposite direction, then you have this interference pattern. So what you should also observe that the spacing of these fringes also depends on how you locate your detector. To look at it in terms of a two-photon process. Because we okay, so let me now try to explain, and I will come back to this later, that how we can understand that we are detecting intensity correlation, the intrinsically two-photon process. And in a two-photon process, it has been very well known from atomic physics that that different kind of interferences are possible. So here we have two atoms which are excited. So one atom can emit a photon, or the other atom can emit the photon, and then the second photon comes out. So this is the initial state of the two atom system. This is the final state. The two photons are here. And we have gone through these two intermediate states. And so when you are looking at the efficiency of a two-photon process, you must sum coherently all possible paths. And since we have these two paths, this one or this one, therefore we have the interference between the independent photons. Okay, another way to understand this interference would be in terms of entanglement. We start with two atoms, each of them is in the excited state. It's a separable state. When we detect one photon, then we produce effectively entangled state of the two atoms. And the detection of the second photon basically is a measurement of the entanglement that you produce in the first step. And so that's another way to understand the interference of two photons is that in the intermediate state,
something called a strange metal, there is something
an entanglement by the detection of the one
metal,
photon.
and there is something called a Fermi
And in
liquid.
fact, the entangled
Now,
state
this strange metal is called strange because it is strange.
an
I mean,
intermediate
that
state
is unlike it is.
does depend on these phase factors depending on the location of the detector and the distances between atoms. And because you have something here which depends on these phase factors, you have the interference pattern. Okay, we can go further and look at the higher order correlation. So, of course, with two photons, with two atoms, we would have just two photons. So we have to add more atoms. So we have, let's say, bunch of atoms. This could be like an ion chain in a trap, and you can have a series of detectors here in the far field, and you can look at these kind of Glauber's higher order correlation functions. So let me just show this figure again with two atoms. And so let us say, suppose you look at with four atoms and four detectors. For certain specific locations of these detectors, one could produce a fringe pattern here which is much narrower than what you do, let's say, in case of G2. And in fact, by an appropriate choice of these locations, for the case of N atoms, you can produce here a fringe pattern which is a factor N narrow. And so we have more fringes by a factor N, and this has consequences for quantum imaging. And in fact, we have a patent on quantum imaging using this technique, whatever is its word. Now we can extend these ideas to interferometry with other quantum systems. And we in fact studied several other systems. We have examined, let's say, the case of two distant Bose condensates, and you can think of doing a light scattering experiment from these two condensates and look at the scattered photons from each of these condensates and look at the intensity correlation between these scattered photons. And this produces basically the entanglement between the collective degrees of freedom of each condensate. Now these ideas can also be generalized to other kind of interferometers. For example, Ramsey interferometer, which was mentioned in the morning several times. And so the idea here in the case of Ramsey interferometry is that you have an atom which is passing, here is the picture. So you have an atom here which is passing through two different zones, and these zones have coherent fields where the atom interacts. And when you look at the excitation probability, then this excitation probability depends on the spatial separation between these two coherent field regions. Now, if you think of doing Ramsey interferometry where these coherent fields are replaced by quantum fields, and for certain type of quantum fields, you find that if you just measure this intensity here, then the interference pattern disappears. So what we need to do is to have a Hanbury-Brown version of the Ramsey interferometer. That is, we have to repeat this experiment where we send these atoms and then here we look at the cross correlations between different atoms. And when you do that, you find well-defined interferences. So now I like to discuss how this entanglement can be used, how the interference can be used for producing the entangled states. So let's generalize the system a little bit. Let's bring in the other degrees of freedom for the atom. And so let's consider an atom with these Zeeman states, so that the excited state can decay either to this Zeeman state or to this Zeeman state. And the polarization of the photon here would be different than the polarization of the photon here. So effectively what you are going to do, you are going to produce an atom-photon entanglement. So this Zeeman state for the atom and the corresponding polarization for the field polarization and the Zeeman state for the atom. And now one can think of putting a polarizer before a detector, and you can choose the orientation of the polarizer. By choosing the orientation of this polarizer before the detector, you basically can project out from here the linear combinations of these two Zeeman states. Okay, so that's the idea we like to use, and now we generalize this to more than one atom to show how the entanglement comes about. And in particular, I want to show you how these quantum interferences among pathways can be used to produce GLG states. Now, I'm displaying this pictorially rather than giving you the details for this production. So supposing we start with all the three atoms in the excited state, and we have three detectors, D1, D2 and D3. The detector D1 has a polarizer oriented at an angle theta 1. Detector D2 polarizer oriented at an angle theta 2. Detector D3 with a polarizer oriented at an angle theta 3. So now, if detector D1 clicks, then this state is going to go into a linear combination of these 6 states with the corresponding phase factors. And now, let's say the second one clicks, and because here we have a polarization at a different angle, so after the second detection, this state is going to go into a linear combination of so many states, and then the third detector clicks, and that's going to produce a linear combination of all these states of the three atom system. So we start with three atoms, all three in the excited state, and by using polarizers oriented at different angles, theta 1, theta 2 and theta 3, we produce a linear superposition of all these. And now we have a flexibility of choosing these thetas, and if you examine these combinations closely, then you would find that if all thetas are chosen such that these are the cube roots of unity, then these boxes vanish. And so you are only left with a linear combination of this and this, which is the state. So what this diagram shows, that three atoms can be prepared in the GHG state, and all I have done, I have basically used this quantum interference between different pathways. Here we have very large number of pathways which are possible, but the quantum interference enables us to prepare just the GHG state. And in fact, one can prepare a variety of other states, but this one I have just given as one illustration of what one can do. Okay, finally, in the last few minutes, I want to discuss the question of quantum interference and the non-locality of the independent photons. Let me quickly go back to okay, the structure of this G2 that we got for the case of two excited atoms, it turns out, and you can prove mathematically, you can use Cauchy-Schwarz inequality to prove mathematically that if this gamma 2, which in this case happens to be this, if this is less than 0, then the underlying field is non-classical. So non-classicality in quantum optics we always prove through Glauber-Sudarson's T function, and we say if we discover that the Glauber-Sudarson T function can be negative or does not exist, then the underlying field is non-classical. So the non-classicality translated into something which is measurable. G2 is a measurable quantity. The T function is not directly measurable. So therefore we always like to translate the non-classicality into some measurable quantity, and it turns out that if this is negative, then the underlying radiation is non-classical. So two atoms emitting independently intrinsically produce a radiation field which is non-classical. And therefore you can also investigate the question of non-locality. Now non-locality, as we all learn, is usually translated or usually described in the spin language. We always consider two spins and the spin-spin correlations. For our system, we have to translate this non-locality to the correlation function for the detection of photons by the two detectors. So this is the correlation function which is basically the intensity detected by the detector 1 and the intensity detected by the detector 2. And from this correlation function, we define a new quantity which we call as C, and the way it is defined, you take this correlation function and average this correlation function over the position of one of the detectors, normalize it and subtract 1. Now this correlation function turns out to have this structure, and the parameter nu is equal to unity for the case of two excited atoms. Once you have this correlation function, then you can introduce in the standard way this quantity B, and then you can follow the standard arguments which are used in the literature to derive the Bell's inequality for these correlation functions. And so for our system of two excited atoms, the corresponding correlation function that goes in Bell's inequality would be this, which adjusts the structure cosine phi 2 minus phi 1, and therefore this would also suggest the non-locality of the photons produced by two independent atoms. We have also looked at a class of other systems. I don't have time to tell you about the experiment, but a number of experiments have been done on interference between independent photons. These include the experiments with neutral atoms, experiments with ion traps, experiments with color centers, and even some experiments with quantum dots. And so what we have investigated is the possibility, I lost the mic, Thank you.
Your feet.
Oh.
You are stepping.
Yeah. So we have investigated a more general class of systems where this could be a single photon source, and the second source could be a more general source. And so then the question is, under what conditions the fields produced by these two sources, as measured in terms of the intensity correlations, would reflect quantum character of the fields. So the second source could be a coherent source, could be a thermal state, or could also be these photon-related coherent state or the photon-related thermal state. In all these cases, we find that this correlation function has non-classical features which can be detected in terms of the violations of this Cauchy-Ford inequality, provided the number of photons in the second source, which is coherent or thermal or photon-related coherent source, is very small. So even if you have dissimilar sources, you can have interferences, you can have non-classicality. So let me conclude. I show the possibility of interference between independent photons. I show how the entanglement can be generated from measurement process. The photon-photon correlations have non-classical character. The atom-photon entanglement is an intrinsic property of the vacuum of the electromagnetic field interacting with the atom. Photon-atom entanglement can be used to produce atom-atom entanglement. I didn't talk about Dicke states, but one can also produce Dicke states. And idea is applicable to other systems. And finally, non-locality of independent sources. Thank you.
Thank you very much. I think it's appropriate, very appropriate to have this talk here.
Thank you.
Illustrating also that the both statistics is a crucial thing in what you're saying.
Right.
Thank you. Very, very nice. We have time for questions.
This is regarding the two atoms interacting the photon.
Yeah.
There will be, in general, an entangled state. So when you are evaluating G2, you are taking the expectation value of the 4 electric field, product of the 4 electric field. So the expectation value is taken with the full entangled state, I guess.
Well, it's a dynamical system. So when we calculate G2, we calculate the G2 for the 2-atom system interacting with the entire vacuum of the electromagnetic field.
Right, so even the atomic states are taken into account when one is taking the expectation value.
So to start with, as an initial condition, the atoms are separable state. Dynamically, they all get entangled.
Right. So the point what I wanted to mention was then you extend it to n atoms, and n in general can be macroscopically large. So now the question is, as Professor Levy pointed out, if you have a macro-realistic theory where there is no entanglement, I suppose that when you are taking the averaging with no entanglement, the predicted result will be different from taking the entangled state.
I'm not making any assumption here. As I said, that's a dynamically evolving system. You put in certain initial conditions, okay, and the rest is done dynamical way.
Well, in reference to this very interesting experiment where you excite two atoms and you observe correlation in the detection of the two photons, I want to signal two things, a very old one and a recent one. The very old one is that, if you don't know it, there is a fantastic calculation by Hugo Fano. You know this calculation? In the early days of Ambridge Run and Twist, Hugo Fano calculated explicitly what happens for two excited atoms, and he, to my knowledge, he was the first to write an interference between the amplitudes associated to two photons. It's an awfully involved calculation because Fano pushed the calculation to the end, and it was published, believe it or not, in American Journal of Physics, that is to say, allegedly a pedagogical paper. But you can recognize in this calculation all the features of this two-photon interference. Okay. Now, on the more recent, there have been several experiments recently, but I want to signal one which was done by Antoine Broes and Philippe Granger, in which there are two independent atoms in two optical traps, and then they are able to merge the two modes associated to the two independent spontaneous photons, send it to a beam splitter, and do the Hong-Wu-Mandel experiment, which shows that when the two photons arrive at the same time in the beam splitter, either both photons go on one side or both photons go on the other side, which is a perfect entanglement, because what you prepare is the entangled states with either two photons on one side or either two photons on the other side. I mean, it's, well, but by either, I mean quantum, of course, superposition.
Yeah, I'm well aware of Philip Granger's experiment. But I just want to mention, since you said,
Of course, you cannot.
just quickly, that this possibility, that you see, when you have two detectors, in my case like this, then there is zero probability.
How does your proposal concerning generalization of the Henry-Brown twist experiment to in particles, in that context you mentioned the possibility of using that for post-condensate.
Yeah.
How does that relate to the actual experiment of Andrews, the famous interference experiment?
I'm sorry, which experiment is this?
The experiment, an early experiment of the MIT group, I forget Kelly's group, on interference of two independent Bose condensates. I just wondered how that was related to the proposals you were making.
You can answer that.
Yeah.
I can answer that question. When you mentioned that one way to interpret the interference which appears in the J2 function when you have two photons emitted, okay?
Right.
One way of interpreting it is to say that when you detect the first photon, you more or less project the global state and fix the bright fringe pattern at this point. And then the next detection will be done more likely on another bright fringe, that is to say at an integer number of fringes from that. And it's, well, you know, when the Ketterle did this experiment, there were two ways of understanding it. The traditional condensed matter spirit said there is spontaneous symmetry breaking, each BEC has a phase, and so there is no mystery in observing the interference. But from the point of view of people coming from quantum optics, we don't think that it is a spontaneous symmetry breaking, and then the first detection of the first atom starts freezing, fixing the fringe pattern.
I agree with the quantum optics point of view.
Oh, you agree with the quantum optics point of view. Thank you.
Thank you for explaining.
I think we're about finishing. Unless there was a quick question from someone else. Otherwise, oh, over here.
Just a quick comment that we have also observed second-order correlation interference with thermal independent photons. But that does not create entanglement. The explanation, well, there's still a lot of debate about this, and it'd be interesting to hear your point of view, whether it's classical or semi-classical or semi-quantum.
So you have two thermal sources, you are saying?
Yes.
Okay.
And you can observe certainly interference, but the visibility is not one.
Yeah, I know. In fact, since you mentioned this, some years ago, we had a collaboration with a group of Aristide Dogeru from Creole, and we wrote an experimental paper published in Optics Letters some years ago, precisely on that problem, that how to determine the object properties by using the thermal light.
Well, I think that brings this session to a close.
Thank you.
Thank you again for your
Thank you.